Okay, today we're going to talk about gravitation. More specifically, we're going to talk about how do you calculate the gravitational force. Now, you might be thinking that we could calculate the force of gravity as F of gravity equals little m little g. And that is one way to do it, but that only works if we know what little g is. And, if we're on Earth, we know that that is 9.8 meters per second squared. But if you're anywhere else or doing anything else, we've got to find a different way to calculate the force of gravity. Now we're going to talk about gravity, and we're going to do some of the calculations that Isaac Newton did in determining the gravitational force. And a lot of it dealt with what the moon was doing and the moon's motion around the Earth. So if we look at the globe in the corner of the room, which is about the size of a basketball, on that scale, how far away do you think the moon is? You can write that value in meters, and also what size, and you could write that either in, the size of that with the diameter in centimeters or inches, or you could even just pick an object that you think's about that size. So for the globe in our classroom that's about the size of a basketball, the moon would actually be under a light in the back corner, or if you think about it on a basketball court, the moon would be about a softball size, about the three-point arc. So what Newton was doing is he was thinking about the moon's motion, and we know that the moon goes in a circle around the Earth, and by looking at that, and he knew the radius of the moon's orbit, which was about 384 times 10 to the third kilometers, and he knew the period of the moon, which was the time it takes for the moon to go around, is about 27 days. With those two things and what we've talked about so far with circular motion, you should be able to calculate what the velocity of the moon is, and then by using that velocity, you should be able to get the acceleration of the moon as it goes around the Earth. So first, to calculate the velocity of the moon, well, I know velocity, we're going to use the idea for speed, which is distance over time. And the distance that the moon travels as it goes around the Earth is the circumference of that circle, which is 2 pi r. And the time is the period, which is 27 days. So we can convert that. We know that 1 day is 86400 seconds in a day. And we can calculate through that using the radius of the Earth that was given on the previous page of 384 times 10 to the 6th meters. Remember, it was times 10 to the 3rd kilometers, but there's 1,000 meters in a kilometer, so we had 3 extra zeros. If you do this calculation, you find out that the moon is traveling 1,034 meters per second. Now that we know the speed of the moon, we can do the acceleration is v squared over r. And we can say that it's 1034 squared over our radius again of 384 times 10 to the 6th. And when we do this calculation, we get 0.0028 meters per second squared. So that's the acceleration of the moon as it goes around the Earth. So back in the 1600s, Isaac Newton's thinking about this, and he's thinking, okay, there's the Earth, and there's a moon accelerating around. It's going in a circle, so it's accelerating. And he's thinking that somewhere he heard the equation F equals ma. So if the moon is accelerating, there must be some force making it accelerate. So Newton sits and tries to figure out what force makes the moon accelerate. So Newton thinks maybe it's an applied force, and actually, back before even Newton, they thought that angels were in charge of moving these planets and moons around by doing these little crank things, and this is an old tapestry picture that shows that. But Newton thinks he doesn't think it's angels and it's not an applied force, so he thinks what other forces could get this to move around. So then Newton thinks it's tension. Maybe that the moon is tied to the Earth with a string, and that string causes the moon to go around the Earth. And he gets kind of upset with his parents that they never took him to Moonstring National Park. And he asks his mom, and his mom says there's no such thing as Moonstring National Park. There's no string that connects to the moon. So he's trying to think, okay, well, what force can it be then that makes the moon go around in a circle? So Newton thinks more about this, and he says, okay, so if I have the ground and if I have a tree and there's an apple in the tree, he says, well, it's the gravitation force that causes the apple to fall to the ground. Well, he thought, where does that gravitation force end? And way out where the moon is, as it goes around the earth, he thinks maybe it's the gravitation force that gets the moon to go around a circle. So Newton starts thinking about these values, and he knows that the radius of the earth is 6.38 times 10 to the 6th meters. And he knows that the radius of the moon's orbit is 384 times 10 to the 6 meters. So he takes the radius of the moon's orbit divided by the radius of the earth, and he finds out that the moon is 60 times as far away from the earth as we are as we stand on the edge of it. And then he looks at the acceleration due to gravity on earth, and he knows that that's 9.8 meters per second squared. And he takes the value that we just calculated for the acceleration of the moon as 0.028 meters per second squared. And he does 9.8 divided by 0.028. And when he does that, he finds that he gets the number 3600. So that means acceleration here is 3,600 times as much as the acceleration of the moon. So he takes a look at these two numbers, and he's trying to find some kind of relationship. And what Newton finds is that 3,600 is the same as 60 squared. So what he realizes is that the gravitation force changes by the square of how far away you are from the center of the earth. And we can write that as gravity is proportional to 1 over the radius squared. So what we find is that as you leave the earth, the gravitational force doesn't just like end somewhere, it just gets less and less as you continue away. So if you build a ladder and you climbed up that ladder and you became 2 times as far away from the center of the earth as you originally were, what would the new acceleration due to gravity be? Well, what we can do is we know that gravity is proportional to 1 over the radius squared. And if we double the radius, we have gravity is proportional to 1 over twice the radius squared, which results in 1 over 4 times the radius squared. So if we double the radius, or double our distance from the center of the earth, we'd have 1/4 of the gravity. So let's look at our earth here again, and let's say we make a ladder now, and this ladder is even bigger. And if we get 3 times as far away from the center of the earth, what would the new acceleration of gravity be? Well, it's 1 over the radius squared, remember, so if we have 1/3, we're getting 3 times away, so it'd be 1 over 3 times squared, so we would get 1/9 of the gravity. And just one more quick example. What if we got from the earth and we ended up climbing so far that we have our little earth and we climb up a ladder all the way and we get 10 times as far away? What would the new gravity be? Well, again, remember it's proportional to 1 over the radius squared. So if we're 10 times as far away, it would actually be 1/100th of the gravity that we originally had. Now I'd like to make you a couple predictions and a review. So I'd like you to answer, how does the distance from an object affect its gravitational attraction? And then make a prediction. What else do you think might affect gravitational attraction? So we know that the Earth has gravity. And we know that the Sun has gravity. And even the Moon has gravity. So I guess the next question is, how much mass do you actually need to have gravity? And again, Newton thought about this, and he thought, what is this magic value? How much mass do you need? And the more he thought about it, he thought maybe there is no magic number. Maybe any mass would have gravity. So this leads to one of the greatest pickup lines, and the idea with this is that you could tell that special someone, hey, I know that you're attracted to me, and as much as they try to deny it, you can say that, with confidence that they're attracted to you. Because according to Newton's law of universal gravitation, all masses are attracted to each other. And what we can do is we can think about if we have 2 people and let's say that they're 1 meter apart. And just to make it easy, let's say that they're each 50 kilograms. So now we know that the force of gravity is proportional to the masses of each object, and we know that it's inversely proportional to the distance between them squared. So that would give us 50 times 50 over 1 squared, and that's 2,500 newtons. But that's a lot of force. That would be about 100 pounds of force pushing on you. And I had a previous student say, is that where the term crush comes from? But actually, there's something wrong with this. Newton thought about that, and if there was really 100 pounds of force on you, you would get smashed together. So what he found was that this really wasn't the full equation, and he needed another piece to add to it. So Newton has this. He has the force of gravity, and he knows that it's mass 1, mass 2. They contribute to the value, and divided by the radius squared. But from our estimate before, we found out that that was just way too big. So what Newton did is he just did what everybody does if they make a mistake, they can't get the right answer. He made something up, and he put this value of big G in here. And this is the gravitational constant. And he really didn't even know what that value would be. He just knew that it had to be something really small so that when he multiplied by the masses and the radius squared, it would give you the actual gravitational force. So what we have now is our equation to solve for the gravitational force. Remember, we could have used little m, little g, but if we don't know little g, we have to use the bigger force here. So this is gravitational constant times the two masses. And then remember, this r is the distance between the centers of the two objects. The value of the gravitational constant, and we'll use this one a lot, is 6.67 times 10 to the minus 11. Remember, I said it had to be something really small. Remember, minus exponents mean there's zeros, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we shift that 11, 6, 6, 7. So that's a very small value that we would use for the gravitational constant.